Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Foundational Mathematics, we want to talk about complex numbers, and why complex numbers are very useful when we're talking about engineering as well as physics. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So before we get started, we'll just introduce every single topic that I'll be introducing here. So we'll be starting with the introduction of why do we need complex numbers. And then we'll go to the Cartesian form of complex numbers. And we'll later also introduce the polar forms of the complex numbers. Polar form of complex numbers. Finally, we will talk about the application of complex number. So here are the timestamps that you can skip throughout this entire video. So let's start with the discussion of why do we need complex numbers. So the idea is pretty simple. Let's say if you have ax squared plus bx plus c equals to 0. This would correspond to a solution where x equals to negative b plus or minus the square root of b squared minus 4ac over 2a. But consider one problem in which if you try to solve x squared plus x plus 1 equals to 0, what you would have is this will equal to negative 1 plus or minus the square root of 1 minus 4 over 2, which is negative 1 plus or minus the square root of negative 3 over 2. Now the question is, what is the square root of negative 3? And so this is where the idea of the complex numbers comes in which you introduce a new number, which you call as the imaginary number, for you to solve this entire equation. And why do we introduce this? Is that when you come to solve differential equations, you would end up finding some things like this, in which it describes a very spectacular phenomena. But we will discuss this throughout this entire video. So let's introduce the idea of the complex numbers in the Cartesian form, or a plus bi, or sometimes you could write this as x plus iy. So this actually corresponds to if you have the imaginary as well as the real axis, and then you would have this number. You could state this number to be in the form of a towards the real value and then b in the imaginary direction. And this gives you the complex number. So let's try to express the negative 1 plus or minus the square root of negative 3 over 2 into this Cartesian form. So to do that, we need to observe a property of the square root. The square root of ab must be the square root of a multiplied by the square root of b. This is always true. So we could express this as the square root of negative 3 is equal to the square root of negative 1 times the square root of 3, or this is I square root of 3. That means that our solution could be written as negative 1 over 2 plus or minus square root of 3 over 2 times I. And this is the Cartesian form of the complex number. So something very useful to talk about the complex numbers is that when you do additions, let's say z1 plus z2, it's simply just adding the components up. Or you could also think of this as just algebraic addition. So something like x1 plus y1 I, you add this up with x2 plus y2 I. And this will give you x1 plus x2 plus y1 plus y2 times I. So this is about simple addition. But what about multiplication? Multiplication also follows the same idea of adding and of multiplying the complex numbers. So you could write this as x1 plus y1i, multiply this by x2 plus y2i. So if you do the multiplication, it straight away gives you x1 x2 plus y1 x2i plus x1, y2, I plus y1, y2 times I squared. But you know I squared to be -1 because that's the definition of I. So this will correspond to x1, x2 minus y1, y2 at this with x1, y2 plus x2, y1 times I. And this is multiplication for a complex number. It also gives you a complex number. But the physical meaning of adding complex number literally makes sense. You're pretty much adding vectors. But what about multiplication? It doesn't really have a physical meaning. Well, you could try to plot it and try to figure out what does it mean. And you could later do this. But I won't discuss it right now because we'll later cover it when we talk about the polar form of the complex number. So with these two information, we could just state, let's say, if z1 plus z2 is equal to 0, or meaning, sorry, z1 minus z2 is 0, or pretty much stating that z1 equals to z2, we observe that the x1 must equal to the x2, and y1 must equal to y2. This is a physical meaning that we see, is that one vector can only be stated by only two numbers, and it cannot be represented anything else other than those two numbers. Another type of property, which pretty much corresponds to negative numbers in real numbers, is something which we call as the conjugate. So the conjugate pretty much states that z equals to x minus iy, z star. So if z is x plus iy, z star is x minus iy. And there are certain properties that you could use with z star. First is that if you multiply z times z star, what you would obtain is the x squared minus plus y squared. You could just do the multiplication, and this actually corresponds to the length of z, which is the same thing as the length of z star, both of them squared. And this is always greater than 0. So this pretty much corresponds to the length of your complex number if you look at it in the Cartesian form. And also what we could gain from the conjugate is that we could actually write certain expression to give us the real value of your complex number. So let's say the real value of z is going to be z minus plus z star over 2. You could do this algebraically and it proves. Same thing with the real part of, the imaginary part of z, which corresponds to z minus z star over 2i. It's also derivable from pretty much expressing z in terms of x plus iy. So we have discussed about addition, subtraction, and multiplication. But what about another fundamental operation, division? So to do an example, let's do 1 over z. And let's try to solve for this. So this could be expressed pretty much as x plus iy, but maybe you could express this in terms of 1 over z, multiply top and bottom by z star. And what you would obtain is that this would actually equal to the z star over the z, the magnitude of z, squared. This is pretty much the definition of doing a division. So you could just multiply this 1 over z by your other z to turn it into some form of a multiplication instead of a division. There are also squaring and cubing, or taking the square root. Everything literally means the same. But there are ways for you to get to that certain type of equation. So let's do a certain example. Let's just state that I want to figure out what's the square root of I. And we'll call this as z1. Maybe this doesn't seem to be a complex number, but it is actually a complex number. We could just square both sides. We could get I equal to z1 times z1. So you could express this in terms of the Cartesian form. It's x plus yi. Let's just use that. X squared minus y squared plus 2xy times I. And from here, what we observe is that x must be equal to plus or minus y, and 2xy must correspond to 1. So this will correspond into much more solution. So substituting it in, we could obtain this to be y squared equals to 1 over the square root of 2, plus or minus technically, but oh well, let's just take it as 1 over square root of 2. And sorry, the y should be 1 over the square root of 2. And this means that you could also solve for the x, which is 1 over square root of 2 as well. So this gives you certain complex numbers that pretty much express the square root of I. It's pretty much 1 plus I over the square root of 2, or it could also be negative 1 plus I over square root of 2. So pretty much the square root of I pretty much corresponds to two different numbers, but it pretty much corresponds to the same square root of I. So this is where complex number becomes much more complex, because certain functions give you certain multiple different answers. So we'll later discuss about this when we talk about complex functions. But for now, we'll just state that the square root of I is 1 plus I over the square root of 2. So there are certain properties about the complex numbers. And something that's pretty obvious is that the real part of z and the imaginary part of z is always less than equal to the magnitude of z. This is pretty much observable straight away. Another thing that I want to note is that the length of z1 times z2 would be, so we could just try to expand this first. So you could express this as the square root of z1 times z1 z2, multiply this by z1 star times z2 star. So if you don't know, a property of conjugates is that if you take the star of this, pretty much everything is also given the conjugate. You could prove this by taking x plus iy. So this pretty much does this property for you. And this will actually be the same thing as the magnitude of z1 times the magnitude of z2. So these two magnitudes will be is a property of complex numbers. Another property of the complex numbers is that if you take the this is the length. So if you try to figure out what's z1 plus z2, this would be equal to the square root of z1 plus z2 multiply this by z1 star plus z2 star. And this would equal to z1 times z1 star, that's the length of z1. Oh, sorry, this is squared. Nah, we could just write it as this. You know what, let's just square it. So if we square it, so it will be just something like this. So we could open this cage up to get the length of z1 squared plus the length of z2 squared plus 2z1 z2 star, sorry, z1 z2 star plus z2 z1 star. And take the, no sorry, we could just do it like this. Now, this is a very interesting property because this is actually, so we could just rewrite everything again. Add this by the real part, 2 times the real part of z1 times z2 star. So if you take the square root now, so this is an important property, but also taking the square root of it, we'll get z1 plus z2 would equal to the length of z1 squared plus the length of z2 squared plus the 2re z1 z2 star. Square root of everything. Now, here's a very interesting trick, is that if you know that the real part will always be greater than the length of the complex number, we could rewrite this as the square root of length of z squared plus the length of z2 squared. We add this by 2 times the length of z1 times the length of z2, because we know that we could separate the conjugates from this property. So this pretty much corresponds to the length of z1 plus the length of z2, everything squared. and then you take the square root, so the square cancels out. So you would get this. So this is an important property of the complex number as well. So now let's try to consider the polar form of the complex number. So let's just start with e to the power of I theta, and let's try to solve this. This is just the sum from n equals to 0 to infinity of I theta over n factorial to the power of n. So this corresponds to 1 plus I theta minus theta squared over 2 factorial minus I of theta cubed over 3 factorial, and so on. So we could rewrite this again as 1 plus 1 minus theta squared over 2 factorial plus theta to the power 4 over 4 factorial, and then the backside it's I times theta minus theta cubed over 3 factorial plus theta to the power 5 over 5 factorial, and so on. What we observe is that this is just the cosine theta, and the backside is I sine theta. This is something that I want you to remember because this is a very useful tool to express complex numbers. So the tool is something like this. R times e to the power of I theta is just R cosine theta plus R sine theta times I. This property is very useful because when we express this in the Cartesian plane, we could just express just the length as well as the angle theta. This is what it truly means. So we could express now what z star is. Z star of R e to the power of I theta star is actually only just R cosine theta minus R sine theta times I. Or you could write this as R cosine negative theta plus R sine negative theta I. So this is just R e to the power negative I theta. You could also do this by actually doing the definition of z times z star. It's just the length of z squared, right? So the length of z squared corresponds just to the r squared, as the length of e to the power of I theta is always 1. So it's just r squared equals to r e to the power of I theta, multiply this by the z star. So you could just solve this. This is going to be r e to the power negative I theta, which also proves the conjugate is just a negative angle. So by definition, the conjugate is just a reflection over the real plane. Another thing is about multiplication. Let's just do this multiplication straight away. z1 times z2. What does that mean? This is just r1 times r2 e to the power of I theta 1 plus theta 2. So it pretty much magnifies your magnitude and also just adds the phase. It's that simple. And what about division? 1 over z, let's say. This only corresponds to 1 over r1. Multiply this by e to the power negative I theta. So you're just changing your phase to the negative, so you're reflecting it, and then you do the reciprocal of the length. So it's pretty useful for you to write complex numbers as its polar form. Another thing that's very useful is that you could actually express cosine theta and sine theta by e to the power of I theta. So cosine theta, from the definition of the real part, is going to be e to the power of I theta, added by the conjugate, divide that by 2. While sine theta corresponds to e to the power of I theta, subtracted by the conjugate, divide that by 2i. It's that simple. And because of this, we could actually figure out what is the value of, let's say, cosine of n theta, or sine of n theta. And the way that you would do this is by actually expressing this as e to the power of I n theta. So you could get the cosine n theta and the sine n theta. And this actually just corresponds to e to the power of I theta to the power of n, or just the cosine theta plus I sine theta. You take this to the power of n. So this is very useful if you're trying to figure out the perfect definition of of a certain angle if you know the value of the other angle. So let's talk about some applications. And one of the most major applications of complex number comes from differential equations. So differential equations, so diff equation, if you are playing with second order differential equation, you would normally see a solution like, the problem to be partial squared of x over psi, let's say, partial x squared. So we could just express, let's say, the quantum mechanics over 2m plus v psi equals to e psi. So how do we solve this problem? So let's just assume that this is just a constant v. So v is always a constant, and then the e is always a constant. And we want to solve this differential equation. So there are ways for you to solve it. But let's just state that this is negative h bar squared over 2m equals to e minus v psi, right? Partial squared psi over partial x squared. And now let's just assume that our e is greater than v. So we'll just denote this right-hand side to be a constant, let's say a, psi, and minus h bar squared over 2m partial squared psi over partial x squared. And a is a positive number. So what's the solution? So one of the solutions that you could get from here is that your psi needs to be cosine or sine. But an easier way just to do it is by guessing easily e to the power of I k times the b, obviously. And if you solve this equation, you could get what the k is straight away. The k is going to be the square root of 2m e minus v over h bar. This is a very useful tool when you're doing quantum physics or circuit theory, signals and systems, and much more. So the idea of differential equations requires you to solve it in a very hard way if you're doing with real functions. But if you do it with complex numbers, you could just solve it with only one value, e to the power of I k. And because this left-hand side and the right-hand side is the same, if you know the answer of the right-hand side to be a real function, you could just take the real part of your function on the left side, and it will still give you the same. It will give you the same solution. You can just check it if you just plug it in as well. So there's also another example that was given on the book, which is damping. So it's like the partial squared of q over partial t squared times L at this by r dq over dt plus q over c equals to vt. Now, if you state that the v is a complex function first, e to the power of ikx, let's say, you could just guess the solution to be e to the power of ikx, and you could solve for the constants, and you would get a complex number at the front, multiply this by e to the power of ikx. And so with this complex number at the front, what you would get is that you could actually change the face of your solution. So you don't need to express lots of the boundary conditions. Instead, all of the boundary conditions is already written within this one complex number. So if you want much more examples, you should try to refer to the book for you to solve these kinds of problems by using complex numbers. But anyways, we'll be talking about differential equations at the future. So this is all for complex numbers. So thank you very much for watching, and make sure to like and subscribe, and also please share this to your friends who really needs to understand the mathematics behind physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.